this episode, we're going to talk about using AI to help build detections, which are the signals and rules that tell defenders something suspicious might be happening. For beginners, detection engineering can sound like a job reserved for specialists who live inside complicated dashboards and write mysterious query languages. In reality, the core idea is approachable. You define what bad behavior looks like, you decide what evidence would show it, and you design a way to spot that evidence reliably without drowning in false alarms. AI can help with each of those steps, especially for new learners who are still building intuition about attacker behavior and about how logs fit together. The risk is that if you let AI invent detections without grounding them in your environment, you can end up with rules that look impressive but do not actually work, or worse, rules that create so much noise that the team stops trusting alerts. Using AI in detection engineering is therefore about using it as a thinking partner. It can suggest hypotheses, help translate ideas into rules, and help refine alerts to reduce noise. But humans must validate detections against real telemetry and real threat models. The goal is to build rules, correlation logic, and noise reduction strategies that are credible, testable, and safe to operate. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to define what a detection is, because beginners sometimes confuse detections with controls. A control is something that prevents or blocks, like access control or encryption. A detection is something that notices and signals, like an alert that says this behavior might be malicious. Detections usually rely on telemetry, such as authentication logs, endpoint events, network flows, application logs, and cloud audit trails. A detection can be as simple as an alert on too many failed logins, or as complex as a multi-step correlation across identity, device, and network activity. The purpose is to shrink the time between an attack starting and a defender noticing. Detections are never perfect, because attackers adapt, and because normal behavior can look suspicious sometimes. That is why detection engineering is a balancing act between sensitivity and precision, meaning you want to catch real threats without creating a flood of false positives. Beginners should see detections as living artifacts. They require tuning, feedback, and continuous improvement, and AI can help accelerate those cycles if you use it carefully. Rules are the building blocks of many detections, and a rule is essentially a statement that says when you see pattern X, raise signal Y. Beginners often assume rules must be extremely complex, but many effective detections start with simple logic that focuses on high-signal behaviors. For example, a rule might flag an authentication from an unusual location, a sudden privilege change, or execution of a suspicious tool. AI can help beginners by suggesting what behaviors are high signal for common attack techniques, and by explaining why certain patterns matter. It can also help translate plain language into structured rule logic, which is useful when a learner knows what they want to detect but struggles to express it in a formal way. However, AI can also oversimplify or overgeneralize, suggesting rules that would generate noise in a real environment. That's why the human must always ask, do we have the required telemetry, and would normal operations trigger this pattern often? A rule is only as useful as its deployability and its noise characteristics. So, AI should be used to generate candidate rules that are then tested and tuned. Correlation is the idea of connecting multiple signals into a stronger story. A single event might be benign, but multiple related events can be suspicious. For example, one failed login might be a typo, but many failed logins followed by a successful login from a new device is more concerning. Correlation often uses time windows, identity linkage, device linkage, and sequence patterns. Beginners can think of correlation like detective work. One clue is interesting, several aligned clues create a case. AI can help with correlation by suggesting which events should be linked and by proposing sequences that match common attack paths. It can also help identify which fields can connect events, such as user IDs, device IDs, or session IDs. The risk is that correlation logic can become too complicated and brittle, producing alerts that never trigger or triggers that are impossible to interpret. A beginner-friendly approach is to build correlation in layers, starting with a simple rule, then adding one or two corroborating conditions that reduce noise. AI can help propose those corroborating conditions, but humans must ensure they are observable and meaningful in their environment. Noise reduction is the discipline of making alerts actionable by reducing false positives and by making true positives easier to recognize. Beginners often think noise means too many alerts, but noise can also mean low-quality alerts that lack context. AI can help with noise reduction in two major ways: improving the detection logic and improving the alert enrichment. Improving logic means tightening conditions, adding exclusions for known benign patterns, and adjusting thresholds based on baseline behavior. Improving enrichment means adding context so analysts can decide quickly whether the alert is likely real, such as including recent authentication history or related process details. AI can help interpret historical alert data and propose where thresholds should be, conceptually, based on patterns. It can also help draft rationale for why a rule exists, which is important because detections are easier to maintain when their purpose is documented clearly. However, beginners must be cautious about excluding too much. Overtuning can remove the very signals you need to detect real attacks. Noise reduction should be driven by evidence. You tune based on observed false positives, not on a desire to make dashboards quiet. A quiet dashboard that misses attacks is worse than a noisy one. A practical way to keep AI use safe in detection engineering is to treat it as hypothesis generation followed by validation. The hypothesis might be, attackers often perform a certain sequence of steps, and we should detect that. The validation step is to check whether your telemetry captures those steps and whether the rule triggers on known benign behavior. Beginners can validate at a conceptual level even without running tools by asking what logs would show, how often that behavior occurs normally, and what alternative explanations exist. For example, a rule that flags every administrative action might catch attacks, but would also catch normal maintenance. So you refine it by adding conditions, such as unusual timing, unusual source, or unusual account. AI can help suggest refinements and explain trade-offs, but it cannot know your organization's normal. That is why baselining matters. Baselining is learning what typical behavior looks like so you can detect deviations. AI can help you think about what to baseline and why, but humans must measure and decide what thresholds make sense. This keeps detections grounded in reality rather than in generic assumptions. Another key idea is that detections should be resilient against attacker adaptation. Attackers change tactics when they know what you detect, and they try to blend in. A brittle rule that only catches one exact string or one exact tool name is easy to bypass. A more resilient detection focuses on behaviors, such as unusual privilege usage patterns, suspicious lateral movement, or abnormal data access. AI can help beginners shift from thinking in terms of specific malware names to thinking in terms of behaviors and objectives. It can also help map detection ideas to attack techniques, which improves coverage planning. But AI can also accidentally encourage overly broad behavioral rules that flag too much. The balance is to define behaviors precisely and to anchor them to meaningful context, such as the asset type, user role, and normal operational patterns. Beginners should see detection engineering as a craft. You are shaping signals into useful instruments, and that requires iteration. AI can speed up your first draft, but it cannot skip the tuning process that makes a detection operationally viable. Using AI can also help with alert narratives, which are the short explanations that tell an analyst why the alert fired and what to check next. Beginners often underestimate how important this is. A detection that fires without explanation is like a smoke alarm that does not tell you where the smoke is. The faster an analyst can understand the story, the faster they can respond. AI can help generate clear, concise narratives that explain what happened, why it might matter, and what evidence would confirm or deny the threat. It can also help recommend what context fields should be included with the alert to support tree-off, such as recent logins, process lineage, or related network connections. The risk is that AI might hallucinate details, so narratives should be templated and based on actual fields captured, not on imagined evidence. For beginners, the key is to ensure narratives are truth-preserving. They should describe what was observed and what is suspected, without claiming certainty. A well-written narrative reduces noise because it helps humans quickly dismiss false positives or escalate real incidents. AI can also support detection engineering by helping manage the detection lifecycle, which includes versioning, documentation, and review. Detections change over time as systems change and attackers adapt. If you cannot track changes, you cannot understand why alert volume shifted or why a detection stopped firing. Good lifecycle management includes recording why the detection was created, what data it relies on, what thresholds were chosen and why, and what tuning changes were made. AI can help draft this documentation and summarize changes in plain language for reviewers. It can also help generate test cases, conceptually, by describing what benign and malicious scenarios would look like in telemetry. Beginners should see this as quality control. Detections are like code, and they benefit from review and documentation. When detections are treated as first-class artifacts, they become easier to maintain and less likely to drift into uselessness. AI can help lower the burden of that discipline by making documentation faster, but the discipline itself must still be owned by humans. Finally, it's worth connecting AI-assisted detection engineering to safety and privacy. Detections rely on telemetry, and telemetry can contain sensitive user information. When you enrich alerts or correlate events, you may increase the visibility of sensitive data. That means detection engineering must consider data minimization and access control. Analysts should see what they need to investigate, not everything that could possibly be collected. AI can help identify what fields are truly necessary and what can be omitted or masked. It can also help classify alerts into risk categories that determine who is allowed to view details. Beginners should understand that security monitoring is itself a powerful capability that must be governed responsibly. The goal is to protect systems and users, not to collect data indiscriminately. A mature approach keeps detection logic effective while keeping privacy risks controlled through careful scoping and retention. This is especially important when AI is used to summarize or interpret telemetry, because summaries can inadvertently include sensitive content. So safe use requires the same care you apply to logging and auditing. Sanitize, redact where appropriate, and restrict access. To close, using AI for detection engineering can help beginners and teams build better rules, stronger correlation logic, and more effective noise reduction by accelerating understanding and drafting. Rules define patterns worth alerting on. Correlation turns multiple weak signals into a stronger narrative, and noise reduction makes detections operationally usable by controlling false positives and providing richer context. AI works best as a hypothesis generator, explainer, and documentation assistant, while humans validate detections against real telemetry, baselines, and threat models. Effective use requires resisting over-reliance, avoiding overly brittle or overly broad rules, and ensuring alert narratives are grounded in observable evidence rather than confident storytelling. Lifecycle discipline, including versioning and documentation, keeps detections maintainable as environments change. Finally, privacy and governance must remain part of the design, because detection engineering uses sensitive telemetry and must be scoped responsibly. When you combine AI speed with human validation and thoughtful tuning, you build detections that are not only clever on paper, but reliable and actionable when it matters.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.